Hey, yo, what's up? Mr. B here. As promised, we're going to be finding the extrema of a function that might require a little bit of math. So I've chosen this function f of x, and I'm going to go through with you guys my process of finding the extrema, and this little function has a neat little thing we can kind of infer from our extrema and derivatives and all of that. But anyways, before we begin in finding the extrema of this function, I'm going to be using red to talk about things involving this function's derivative, and blue to talk about things involving f of x, not its derivative, right? So here I'll start off just like, underline that. Okay, that's blue, right? My way. All right, so first step I always like to kind of embark on when we are solving for extremas. I like to find f prime of x right away before I set up my number line or anything, or try to think about what this function looks like. So let's find that. F prime of x. Now there's nothing really special here. I didn't choose a super complicated derivative because I wanted you to be able to look at this and just be like, yeah, this is continuous right here. Don't have to do any thinking, no graphing, no debating. This is continuous everywhere. So let's not worry about continuity. Let's just worry about the process of finding extrema, because that's what this video is for. In case the last one was unclear, or in case you'd like an example to kind of go along with more of the conceptual stuff I talked about in the last video. Let's find the derivative. Using our power rule, it's just going to be 4x cubed plus 6x squared, and that's it, right? This power comes out in front, and then we subtract 1. This power comes out in front, multiplied by that 2, also subtract 1. Okay, so we found f prime of x. And if you want to, because this might help, if you remember, we're finding our critical numbers eventually, so we're going to set this f prime equal to 0. We could factor out an x squared. That might make things a little bit easier in the future. I think it will. So this is our derivative right here. Okay, good thing to think about as well. Our derivative is also going to be continuous everywhere, and most importantly, well, as such, it's also going to exist everywhere, right? Because if it's continuous everywhere, it has to exist everywhere. Existing is one of the conditions for continuity, if you remember back to one of our first videos, right? So now let's begin. We can draw a number line, or in my case, I like to find critical numbers first, right? Critical numbers. So critical numbers are going to involve really both our derivative and our original kind of parent function here, because it's the critical numbers of f of x, but we're finding where the zeros are, or the locations where f prime of x does not exist, right? So we're going to set f prime of x equal to 0, and we're going to set f prime of x to where it does not exist, but we've already decided that, or we've already concluded that f prime of x exists everywhere here. So no dispute about that, it exists everywhere. So I'm going to kind of scroll down. I'll keep our derivative so you can see that. But anyways, yeah, let's just set f prime of x equal to 0. And I'm going to use this factored form because it'll make this a little bit easier solving for when these, or what these x values are. Okay, so just from this x squared here, we could solve x squared equals 0. X is going to be equal to 0. Okay, so we're going to have a critical number here at x equals 0. But then we also have to account for this like parentheses term, this quantity. We get 4x plus 6 is equal to 0, because that is also, or that also could make this equality true. We could get 4x is equal to negative 6, meaning x would be equal to negative 6 over 4, which is equal to negative 3/2, or 1.5, and that's negative 1.5, right? Okay, so we have our critical numbers, 0 and 1.5, negative 1.5. Now, my next step really for solving these is making our number line with our critical numbers as kind of like little like tick marks on our number line, right? I'm going to have 0 be right about here. I'm going to have negative 1.5. And these are all x values, input values, right, of both our derivative and our parent function, right? But now, and as I briefly discussed in the last video, I always like to have kind of like a little f of x tab, if you would, and I like to have an f prime of x tab, so that we can see what's happening because we have to plug in these variables to our function and our derivative here, not necessarily our function unless you're trying to find the output value of an extrema, right? And I guess down here, I'll write like shape or something, whatever helps you, right? And again, as I discussed in the last video, we're going to be picking input values between and outside of our critical numbers, and we're going to plug those into our derivative. It's really, really important that we're plugging these into our derivative, not our function, right? We don't want an ordered pair, we want a slope on either side, right? So I think the simplest value we could pick for in between, because I'll start in between here, is probably -1. So we're plugging in f prime of -1. So I'm going to go down a little bit so that we can solve. Okay. In case you would like, I'm going to write f prime of x back up here, up here. F prime of x was equal to the original form. Let's go with 4x cubed plus 6x squared. That was our f prime of x. We found that, right? And so f prime of -1 is going to equal 4 times -1 cubed plus 6 times -1 squared, which is going to equal this -1 to the third power is going to be -1, so -4, because we multiply that, then plus -1 squared is 1, so plus 6, which is going to be equal to 2, and that is a positive value. It's very important that that is a positive value. So we go back up here to our derivative. That is a positive value, right? Which means f of x is going to be increasing here. And the little shape of our graph probably going to look something like that, going up. Just, I like to draw a shape so that we could see kind of here at these extrema, or my bad, critical numbers, what happens to our function. Now I'm going to, let's start on the left here. Instead of -1.5, outside of that, let's pick -2, right? This could be any value. Now I brought a calculator to help me. If you could do this without a calculator, that's awesome. You probably can. 4 times -2 cubed plus 6 times -2 squared. Okay, this is f prime of -2, right? Because remember, we're plugging this into our derivative. We're going to find what's happening to our function f of x to the left of -1.5. Because remember, our critical numbers are the only places in which our function can switch direction, or our derivative can switch sign. So we are 100% confident, we can guarantee that every derivative value left of x equals -1.5 will have the same sign. There are no discontinuities. These are our only two critical numbers on this function. All right, let's kind of bring this back down. Okay, -2 cubed is -8. 4 times -8 is going to be equal to -32. -2 squared is going to be equal to 4 plus 6, or times 6 is 24. And I can already tell that's going to be a negative number, right? So let's go back up here. F prime of x is negative. Oh, here, I should put this. This is equal to -8. I forgot to write that down. Yes. This f prime of x is negative. Every single input value to the left of -1.5 will have a negative derivative and a decreasing function. Our function is decreasing everywhere to the left or lower than x equals -1.5, right? So we already know that we have an extrema here at x equals -1.5. And since our function goes from decreasing to increasing, we're going to have a relative minimum, right? And that's why kind of drawing this shape helps. But you can always use the reasoning there, because f of x goes from decreasing to increasing, we have a minimum. Because f prime of x goes from negative to positive, we have a local minimum, right? But now let's solve for up here. We could pick any value right of 0. I'm just going to pick 1 because that'll be nice and easy. F prime of 1 is going to be equal to And I don't think we need to do this. I don't need to write this out. You guys know it's going to be 4 plus 6, right? All those x's equal 1. That's equal to 10, which is a positive value, right? Now, I kind of talked about this in the last video. We can go from increasing to increasing at a critical number. That is possible. This function f of x, right, roughly looks like this, right? Looks something like that, right? And I chose a function that would have both a minimum and a critical number in which no extrema happens. So here at this point, we have a horizontal tangent right about here, right? I'm trying to draw it. We have a horizontal tangent right about there, but our function just stays increasing. Okay. And now, oh, these are arrows. They go off forever. But now that I've shown you this function, and looking at this number line, we found the extrema. We have a relative minimum, at x equals negative 1.5. And that's it. Those are our only extrema. But if we look at this function, what can we tell about absolute extrema? Well, there's no absolute max because these arrows go up forever. This function shoots out towards positive infinity both directions. Never ends. But down here, the local or relative minimum we found also happens to be an absolute minimum, right? But we can see that in our number line as well. Because remember, at critical numbers are the only places where your function can change direction, right? And so if our function is decreasing everywhere to the left of 1.5 and increasing everywhere, increases absolutely everywhere, past x equals negative 1.5, we can conclude that this must be an absolute minimum, right? Let's say we did a very, very complicated derivative, a very complicated function, where we had a number line with eight critical numbers on it, right? And we had a similar setup, negative value to the left of 1 and positive value to the right of this critical number here. If all of our critical numbers, past, I guess this one, showed positive numbers, positive slopes past them, sorry, I'm kind of confusing here. This applies to every function, right? Let me try to simplify it down. Let's say we had 8 more critical numbers, right? Sorry for my sloppy drawing here, but the derivative was positive for all of them, meaning the function increases everywhere past this. We could conclude the same thing, that this is an absolute minimum. However, if even one of these critical numbers shows a change, right, an extrema, we can no longer conclude that. Because, for example, if you're not really given a function, if you don't do any experimentation, right, you, hypothetically, a function could decrease very, very fast in a very, very short interval, and so you couldn't really conclude anything about this. But it's also true that your function could decrease a very shallow amount in a small interval, but that you cannot be certain about if an extrema is an absolute extrema unless you only have one instance of change, right? If a function if this function were to ever decrease again, we could not conclude that this is an absolute minimum, right? And so I hope that kind of makes sense. I'm thinking of another last final way to explain this, right? The textbook definition, I guess you would see, is you may only see a sign once on this number line, right? Or this this test, right? This is what we would call a first derivative test. You might hear that in a calculus class or see that in a textbook somewhere, right? First derivative test for slope, extrema, and critical numbers and all of that. Our first derivative test will only ever show one negative or one positive value, one extrema, right? Then we can be for absolute certain, or absolutely certain, I tried to say two things at once there, absolutely certain that there's an absolute extrema here, right? But then obviously, just looking at this graph, it is pretty easy to tell that this relative minimum is also an absolute minimum. So yeah, sorry for keeping you here for so long. Before this video gets any longer, thank you very, very much for joining me. I hope this cleared some things up. This is my thought process for going through and finding the extrema of a function using its derivative, critical numbers. And a number line. I think the number line is a very helpful indicator or a very helpful method for learning this and applying this. We could see how our function changes, plot everything down, keep track of everything. Because really there's a lot going on here, even though we only have two critical numbers and a very, very simple function, right? So thank you for joining me, class. Goodbye.